So, hello everyone. This morning we're having the next in our series of seminars. We've got Haroun Mahgerefteh from University College going to talk to us about CO2 transport. And as I quizzed him before he came on, Haroun is someone who likes to explode CO2 to make sure that by understanding what happens when you do it, but of course you don't do it when you're actually transporting CO2. I'm sure everybody knows that probably a pipe of CO2 is what actually most of the public will see when we're implementing the clusters. So it's clearly a very important area. So I won't say any more about it other than say we're very lucky to have Haroun talking to us, and I'm looking forward to hearing what he has to say. As usual, we'll have a period where we just essentially present, and then we'll turn off the recording and have an open discussion afterwards. Okay, floor's yours, Haroun. Thank you very much.
Hi, good morning, John. Good morning, everyone. Thank you for your invitation to speak today. And I'll move on to my first slide. Basically, the topic of this talk is on the CO2 transport aspects as part of this seminar series. And I'll cover the general background and the points of concern regarding the transportation of CO2. So the contents of my talk here is presented in the form of 5 bullet points. First, I will cover the importance of reliable and safe and least cost way of transporting the large amounts of carbon dioxide as part of the carbon capture, utilization, storage chain. Next, I'll explain how the UK is placed for offshore transportation of CO2 for permanent subsea geological storage as compared to Europe. We are no longer part of Europe, so it sounds a bit strange, but here we are. What is special about the properties of CO2 that causes some concerns that we need to be aware of? And I'll then go on to talk about the different methods for transporting the captured CO2 for geological storage. Of course, there are several ways of doing it. Pipelines, ship, trucks, rail, they all have their pros and cons, so I'll be covering those in general. And then I will finish up with shared pipeline networks, CCUS industrial clusters, and hubs. So we all have heard about net zero CO2 emission, and unfortunately, there is a lot of misconception in the public when people talk about, and I've heard it said on the news that when they say net zero, people are explaining in the context of emitting no CO2 whatsoever. Of course, that's crazy. If no CO2 being emitted means that we all, nobody's going to live. CO2 is going to be emitted. The task and the challenge is to reduce it, or ultimately to reach net zero CO2 emission. That is, by definition, is that when we reach a situation when the amount of the CO2 that we add to the atmosphere would be the same as the amount that we remove. So that's what the net zero emission quest is. Now, let's look at the size of the challenge. What challenge we are faced with to reach this net zero emission target? And we've all heard, there are different dates for reaching net targets for reaching net zero emission. It was originally, the aim was to reach it by around 2050 and then 2040. So some people are talking about reaching net zero by 2030. But anyway, here is a presentation of how the amount of CO2 that is released in the atmosphere per every 10 years, beginning from 1970s up to 2100 scaled here. And how it has increased. So by around 1970, we were emitting around 15 billion tons of CO2 per year. And as you can see, this amount of CO2 that is being released, emitted into the atmosphere has dramatically increased, and we are around 45 billion tons of CO2 being released at present into the atmosphere. To reach net zero emission by 2040, this is the path that we should be following. And by 2055, this is the other task. Now, if we aim for the 2040 target, that means that we need to remove approximately 45 billion tons of CO2 per year. It's a major challenge. And there are several ways of doing it. One of those methods, which has found increasing popularity and considerable promise, is carbon capture, utilization, and storage. And it has been estimated that CCUS can mitigate as much as 90% of this CO2, which is being released by burning fossil fuel in electricity generation and industrial processes such as steel and cement production. So CCUS has a major role to play, and to reach the net zero emission by 2040, for instance, it cannot be done without CCUS. So that's something that we need to bear in mind. Now, you capture all this amount of CO2, you need to send it for storage, so you require a safe and economic method for transporting this huge amount of CO2 for geological storage. So why is UK in a fortunate position for CCUS? Why is UK uniquely placed for CCUS? This is the data provided by the British Geological Survey. And UK has a theoretical storage capacity of over 70 billion tons. The majority of this capacity resides in the saline aquifers. This gives UK one of the largest storage potentials in Europe. And here is a very comprehensive and very useful map here of basically where we stand regarding potential storage areas in the North Sea. And as you can see, there are several of these. Many of them are saline aquifers, some depleted hydrocarbon fields with different capacities ranging from 10 up to 4,000 megatons capacity, clustered relatively closely to the shoreline in the UK. And many of these emission sources also happen to be within reach of these potential storage sites. So we have a win-win situation. Our major CO2 emitters are close to the shoreline, and also the storage locations are within relatively easy reach. Here is another map, which basically same data but produced in context of the amount of CO2 and the various indices which is being released for the UK. Here we have a map of major CO2 industrial emitters, clusters. There are 5 or 6 of them here, the major ones, covering different emission industries, refining, fertilizers and chemicals, Grangemouth, for example. You have the Teesside cluster, chemicals, fertilizers and utilities, Humberside. We have Southampton, South Wales, and Merseyside, the major industrial clusters, all emitting huge amounts of CO2. Again, several of these are located close to the shoreline for offshore storage. Now, what are the challenges associated with the transport of these huge amounts of CO2? Now, CO2 is a gas under atmospheric conditions, and the huge amounts involved, it must be compressed prior to its transport to the storage site. We have no choice. I mean, it would be inconceivable to transport the CO2 under atmospheric conditions. So you've got to compress it. And if you compress it, compression requires energy. Energy costs money. And as much as 12% of the energy produced by a power plant may be consumed for CO2 compression. So you need huge compressors for compressing the CO2. And these compressors require power, energy, and hence establishing efficient compression processes, multi-stage compression processes to reduce the compression power requirement is a major consideration for the transport of CO2. Now, there is another issue with CO2. It is a peculiar fluid. And what do I mean by that? Well, it is, as far as its safety is concerned, it is a toxic gas at high concentrations, as well as being an asphyxiant. Denser than air at concentrations greater than 10% volume per volume, loss of consciousness occurs in about 10 to 15 minutes. At greater than 25% volume per volume, it can be lethal. Basically, it displaces oxygen. It's like drowning. So if you are exposed to high concentration of CO2, there isn't enough oxygen, and it's like, it's the lack of oxygen, much the same as drowning. So, and the problem is that it is this dense gas. So if there is, in the unfortunate situation that if it is released, then the gas will linger around for quite a while before disperses. So that is, the safety is a major consideration. The other issue is that, which is actually an advantage, is that liquid CO2 has a density higher than water. And this, coupled with its gas-like viscosity, makes the pipeline transportation above its critical point more attractive as compared to the gaseous state. So you get the best of both worlds. Basically, it is dense in the liquid state and it has a low viscosity. If it has a low viscosity, that means that the frictional losses during pipeline transportation are going to be less. So you require less energy to transport it as compared to conventional liquid. And here is a phase diagram for carbon dioxide. Basically, it's a variation of pressure versus temperature. It shows the state of carbon dioxide at different temperatures and pressures, starting, for example, from atmospheric 1 bar pressure up to 10,000 bars. And the temperature from 200 degrees Kelvin up to about 400 degrees Kelvin. So by reference to this diagram, we can tell at any given temperature or pressure, what is the status, what is the phase of our CO2. So here, for example, if we lie at any temperature or pressure, in the gray area, we have gas phase CO2. We move up at 250 degrees Kelvin, for example, and at any pressure just about 20 bar, then we hit the liquid region. If we increase the pressure even higher at that temperature, then we form solid CO2. And we can go back, reduce the temperature, and you can produce solid CO2. So the optimum operating range for transporting CO2 is in this region where the density is high and the viscosity is relatively low. You pack in more of the material and the viscosity is going to be lower, and hence the frictional losses are going to be less. Now, there is another issue, and it gives rise to a safety concern. If you decompress CO2, so if you can imagine a situation that you are transporting carbon dioxide or storing it under high pressure, and you blow down, for example, due to an emergency situation, or there is a leak, then what happens is that the carbon dioxide will depressurize. When you depressurize a gas, it expands, and as it expands, its temperature drops. For CO2, the degree of cooling following expansion, its expansion can be quite significant. So you can have a situation where you have, for example, CO2 at a temperature around room temperature and at a pressure of, let's say, 40 or 50 bar. If you rapidly expand it, you can follow either one of these paths, depending on the expansion trajectory that you follow. You can go along this line here, and then you cross the phase, you hit the phase transition boundary, and you end up with solid phase CO2. Or you can follow a trajectory depending on how fast you decompress, where you end up still in the gaseous state, but in both cases at very low temperatures. So the temperature of the CO2 can reach as low as -70 degrees C. In fact, we have observed this, we've measured it, and you do indeed measure such low temperatures, reach such low temperatures. And the problem with reaching such low temperatures is that if the gas reaches such a low temperature, then any metal in contact with it will also be cooled. And metals are not very good at low temperatures. If you reduce the temperature of steel to -70 degrees C, it becomes brittle and it can fracture. So that's something that we need to be worried about. You could also follow another, when you decompress, follow a different path depending on how fast you decompress, where you cross the phase boundary, move along the phase boundary, and you end up at point B, where you form solid CO2. And solid CO2 can accumulate during accidental rupture, for example, as solid, and it gradually sublimes into a gas phase. And that can cause serious hazards, these situations, due to the sublimation, slow sublimation and slow dispersion of a CO2 gas cloud. And if you happen to be in the vicinity of that, can be hazardous. Also, if you are depressurizing the CO2 in the pipeline through a relief valve, then the valve can also block. So you also have an additional problem. Again, these are very peculiar and also confined to CO2 as a special gas, a special fluid. So having familiarized ourselves with the challenges that we are faced in terms of the extent, the amount of CO2 that needs to be transported, the special properties of CO2, and the safety concerns. So how do we get from the emission source, from A to the storage site? What are the transport options? And there are several. We can capture this CO2 and transport it through, compress and transport it through high pressure pipelines for ultimate geological storage. We can use ship transport or by barge, or we can use truck transport. By far, the most common and the most cost-effective way of transporting the CO2 is going to be through pipeline transportation. So I will focus mainly on the pipeline transportation issues, and I will briefly cover the other modes of CO2 transport, which are a much slower scale. Pipeline transport. Pipelines, as I said, are likely to continue to be the most common method for transporting the very large quantities of CO2 involved in CCUS. There are already millions of kilometers of pipelines around the world that transport various gases, including CO2. So it's transportation use of gases and fluids through using high pressure pipelines is established and safe technologies, which is well known. In the UK, the National Gas Transmission System currently operates about 6,800 kilometers of onshore gas pipelines at pressures of 70 to 85 bar, and some of these have been designed for operation about 100 bar, which is the range of operations that we may want to transport the CO2. Some of the decommissioned natural gas pipelines could be used for CO2 transportation. In fact, the National Grid in the UK have conducted numerous experiments and tests to test the suitability of using the existing stock of natural gas pipelines for CO2 transportation with considerable success. So that is going to reduce costs. So we don't have to build all new pipelines for transporting the CO2. And now there are issues that we need to be aware of for using natural gas transportation pipelines for transporting CO2. The pipeline design operation, typically for several of these are below 80 to 90 bar, although some are up to 100 bar. So we need to be aware of that if you want to transport the CO2 at higher than 80 to 90 bar pressure. We need to bear in mind the age and estimated lifetime of the pipeline. These pipelines have a limited lifespan up to half a century. So some of these have been in operation close to that time limit. So we need to be aware of that. And also fracture behavior, the propensity to fracture behavior and the degree of pipeline corrosion. Now, again, as I will show in the next slide, CO2 pipelines have peculiar properties, thermodynamic properties, which make their transportation using pipelines prone to running fractures. It is of a higher degree of concern for transporting CO2. Fracture propagation is a higher concern in CO2 pipelines as opposed to natural gas pipelines. So that's something that we need to be aware of. And there are, in fact, several projects which are considering using existing stocks of natural gas pipelines for CO2 transportation. So this is a very interesting plot which shows the existing CCS operations. For some are for enhanced oil recovery, many of them in the US and Canada, some which are operational, some are which are planned, and some are which are cancelled. Shows the pipeline capacity versus pipeline length for these different CCUS projects and enhanced oil recovery projects across the world. So you can see the length varies, for these different projects varies anything from a couple of kilometers up to about 900 kilometers, Cortez, for example, 900 kilometers, and the capacities can be up to about, for any of these projects, can be up to maximum of, some of these projects is up to about 90 or 80 megatons per year. So there is experience associated with transportation of CO2. But we still have a long way to go. The estimated CO2 transportation infrastructure to be built in the coming 30 to 40 years is roughly 100 times larger than currently exists. So we have a lot more work to do to be able to transport the huge amount of CO2. So we need the infrastructure to be built, to be put into place, to be able to handle the large amounts of CO2. I alluded to safety issues. As I explained, the rapid expansion of CO2 following its decompression, for example, as a result of a leak, may reach to temperatures as low as -70 degrees C. This can lead to different types of fracture, brittle fracture, for example. The pipeline material will be cooled as a result of exposure to these very low temperatures. Here is an experiment that we conducted as part of our European project CO2 Quest, where we actually instrumented a pipe with thermocouples, and we punctured the pipeline, and we measured the temperature at the surface of the pipeline to see how low the temperature would reach. And I'm trying to see if I can run this. Yes. So here is, on the left-hand side, you can see the scale. Anything in the dark region reaches the gas is reaching up temperatures of -12, around -12, -13 degrees C. And as you can see, the surface of the pipe wall material is also reaching similar temperatures up to -12 degrees C as the CO2 is being released. This is an infrared video of the release process to give us a good handle of the types of temperatures that we reach. So you can imagine a situation if the temperature of the pipe wall reaches the ductile to brittle transition temperature, then the pipeline material becomes highly brittle and it can fracture. Here is a plot of the energy absorbed following impact as a function of temperature. So you can think of this as the pipeline fracture toughness as a function of temperature. As you can see, as you reduce the temperature, the pipeline fracture toughness reduces. If you hit the ductile to brittle transition temperature, there is a dramatic drop in the pipeline fracture toughness, and then the pipeline material very quickly becomes brittle. Here is a video of the behavior of a pipe. Let me try and expand this here. So we are applying stress to the pipeline, to the pipe wall material. Here you go. So that's a pipe material around room temperature. So as you can see, this is what we call a ductile fracture. The pipeline material absorbs quite a bit of energy and you get a relatively slow fracture, ductile fracture. Now the situation becomes quite different. If you lower the temperature now, same pipeline material, but this time, so same pipeline material at a lower temperature, -60 degrees. As you can see, very quickly a crack propagates. And this is a very dangerous situation, which can happen, may happen in practice due to the low temperatures reached. And so this is one of another issue associated with the transport of carbon dioxide in the case of a small puncture, which may not be noticed and which can result to a running brittle fracture. We can also have ductile fractures. CO2 has a high saturation pressure. This poses the risk of ductile running fractures for CO2 pipelines. In the case of pipeline material fracture, is not sufficiently high. So as if the pipeline track tip pressure, which is the saturation pressure, is higher than the crack tip pressure, the crack will propagate until such time that the crack tip pressure is equal to the pipeline arrest pressure. Now, if that track tip pressure is much higher than pipeline arrest pressure, it will propagate over large distance, and you can end up with a long running fracture, catastrophic running fracture, because of the high saturation pressure for CO2. We can have, in the presence of water, we can have corrosion due to the formation of carbonic acid, or we can have hydrates which can form solid hydrates which can block the resulting pipeline blockage. Also, another issue with CO2 is that in reality, the CO2 that you capture is not going to be pure. It's going to contain certain amounts of impurities depending on the capture process. Now, these impurities have a pronounced impact on the phase behavior of CO2. So here is the phase diagram for CO2. The black line shows the phase behavior for pure CO2. If you include only 5% hydrogen in the CO2, as you can see, you end up in a two-phase region where at a pressure of 10 bar, you can have a wide ranges of, at a temperature of 10 degrees C, for example, you can have a very wide range of pressures where you can end up with two-phase CO2, gas and liquid, present at the same time. If you add more impurities, such as typical impurity can be methane, then you can still see a significant impact of the impurities. And the problem is that if you have such impurities, you'll end up with two-phase flows, and compressors don't like transporting CO2 in the under two-phase conditions. They fail. So that's another issue that we need to be aware of, avoiding two-phase flow for CO2 transportation. The other method of the transport is ship transport. Under certain scenarios, ship combined with pipeline CO2 transportation can make economic, can be economically favorable, providing additional flexibility. There are several projects, the Cork CCUS project, Ireland and North Sea Port, they are looking at combined pipeline and ship transportation of CO2. Transport of CO2 by ship is in much smaller volumes as compared to pipeline transportation, and is currently already practiced in industry. So that bear in mind, there's no way that we can transport the huge amount of CO2 that we require for CCUS just by ship transport, but ship transport has, of course, its place. For ship transport, you liquefy the CO2 in the liquid state by lowering the temperature at lower pressure. So ship transportation of CO2 is at lower temperatures compared to pipelines, and also at lower pressures. And already liquefied petroleum gas tankers are used and can be used for CO2 transport. Here is a very useful diagram. It's quite old, but still applicable, which shows the advantages of ship transportation or pipeline transportation as a function of distance in the context of costs. This is increase in cost as a function of the transportation distance. As you can see, this is for offshore transportation. If you go anywhere above 1,000 kilometers distance, then offshore transportation becomes the most expensive method as compared to onshore transportation. If we compare ship transport with onshore pipeline transport, so as we can see, for distances up to about 1,500 kilometers or so, onshore pipeline transportation is cheaper than ship transport. But if you go above 1,500 kilometers or so, then ship transport costs are less. River or barge transport. Barges have been used for transport of liquid gases for many decades. Barges may have cost and regulatory advantages over CO2 pipelines in certain circumstances. CO2 can also be transported in tankers. Now, we need cost, as I mentioned, is a major issue for CCUS. We need to lower costs. And one way of doing it is in the form of industrial clusters. Now, as it happens, many industries are in clusters, are localized. Many CO2 emittance industries are in clusters. So there is a lot of consideration, and in fact, plans afoot, very advanced stages for connecting these CO2 emitters, which are relatively localized, different industries, cement, steel, for example, fertilizers, refineries, capturing the CO2 in these clusters, transporting them via pipelines to a main trunk pipelines, and for storage into a single or multiple storage sites. Because we are using a common transport infrastructure, then the costs are going to be significantly lower. So industrial clusters offer significant advantages. And again, as it happens, UK is in a very fortunate positions because there are several industrial clusters. Here is a map of these industrial clusters where close to offshore storage sites, where there are plans afoot for connecting these different clusters, different emitters in the form of industrial clusters, and transporting the captured CO2 for offshore storage. There are not just UK, but also several industrial clusters across Europe with huge amounts of CO2 which is emitted from these, which can be collected and transported in the form of industrial clusters for storage. These anywhere ranging from Belgium, France, UK, Germany. These are several of these clusters, and ranging anything from 7.6 up to a maximum, the Mersal in France, of about 35.5 megatons per annum amount of CO2 which is being emitted from these CO2 emission industrial clusters. Here is the an example of industrial cluster in the UK, the Teesside Net Zero Northern Endurance Partnership. It's the world's first carbon industrial cluster, which is aimed to be completed by 2030. We have several emitters, fertilizers, for example, hydrogen production, biomass, power stations, all are within localized distant close proximity of one another. These plans are to connect these via pipelines, transport the CO2 via shared pipeline to offshore storage. Here is another example in Europe. It's a North Sea port cluster in Ghent, Belgium. It's designed to capture and transport up to 10 million tons of CO2 per annum. I'm involved in this project in the C4U Horizon project, where we are actually looking at the design of the pipeline and the pipeline cluster for capturing the CO2 from several of these emission industries for transport offshore, ultimately in the Dutch coast, with the potential to capture up to 10 million tons of CO2 per year. So the plans are there. Several of these clusters are at advanced design and conceptual design, and also detailed design stages. Now, the monitoring and optimal control of such complex CO2 transport networks presents several challenges. So it's not as easy. We need to consider several issues. And these are that some of the emission sources may have relatively low purity CO2 and low flow rate. Other emission sources may have relatively high CO2 purity and high flow rate. There will be also likely temporal variations in the CO2 fluid flow rate. So some of these sources may be emitting CO2 continuously. Some of them may be emitting CO2 during daytime and not at nighttime, for example, or not so much at nighttime, such as power plants. So that can be an issue in terms of the control of these clusters. And on top of it, CO2 impurities that may be tolerated in the pipeline may not be tolerated during storage. For instance, hydrogen is a problem during pipeline transportation because it can cause brittle fractures. But during storage, it's not so much of an issue. Similar arguments apply to nitrogen. Trace metals, for example, if you are storing CO2 in aquifers, you cannot have trace metals. Trace metals can accumulate and result in contamination, but during pipeline transportation, are an issue. So as you can see, the control of these structures, these networks, is also a major concern. And to top it all, we need a relatively stable flow of fixed purity at the injection site, in the storage site. You cannot stop the flow into the injection site because you don't have CO2 which is being captured during a certain days. You cannot close the system. The injection site, the storage site, needs to have a stable flow rate and of a fixed purity. So there is quite a bit of challenge, and there is a lot of work which is being done in order to reach these optimum conditions where you can satisfy all parts of the chain. And finally, This is a project that I'm involved with as a coordinator of the Horizon 20 project. Its main focus is capturing CO2 from the steel industry. Steel industries is by far the biggest CO2 emitter of all industries, and it's remarkable. For every ton of CO2 for every ton of steel that you emit almost twice as much CO2. So it's phenomenal. It's a huge challenge. And many people believe that if you are going to hit the target for net zero emission, we need to tackle the emissions of CO2 from steel plants. So in this project, it's a very large project. We have 22 partners across Europe with a budget of approximately 14 million euros, where we look at the main aspect is looking at high TRL capture technologies at low cost for capturing the CO2. We look at one of the main issues that we look at is the network, because these plants that we are capturing the CO2 are ArcelorMittal in the North Seaport industrial cluster, where there are several emission sources. We are capturing the CO2 from all these emission sources using a common pipeline infrastructure. So our role as UCL is the design of the industrial cluster so that we can understand the flow behavior, the temporal variations, the flow behavior, and how the CO2 quality and purity will change as a function of the capture quality, and how to ensure the optimum operation of this industrial cluster. So I finish here, and if there are any questions, I'll be more than happy to answer. Thank you very much.